So far we have discussed about the diamagnetism and paramagnetism. Diamagnetism is due to induced dipole moment, whereas this paramagnetism is because of permanent dipole moment, magnetic dipole moment. And this not only paramagnetism, but other ferromagnetism ferromagnetism then antiferromagnetism and ferrimagnetism ferrimagnetism. So, all are due to the permanent dipole moment. So, what are the difference? What are the difference among them? So, basically in this paramagnetic material, so their dipole moments are there, permanent dipole moments are there. So, all are differentiated based on the ordering of the dipole moment in the materials. So, in this case, if this ordering are like this random, ordering are random, okay, spin are randomly oriented, and without for h equal to 0, for h equal to 0. So, if these dipoles are oriented like this, so net magnetization is 0. Okay, net magnetization is 0, and if moments are dipole moments are oriented like this, if they are oriented like this, okay. So, they are pointed in same direction. There may not be parallel, all are parallel, but they may be also parallel. So, for h equal to 0, this is the case, h equal to 0, and in this case you will get net moment along this direction. So, m is not equal to 0, okay. So, then this we tell this ferromagnetic material. On the other hand, if the arrangements are anti-parallel, so number of dipole moments are up and number of dipole moments are down. So, then net magnetization is 0, and this is also for before applying magnetic field. Okay, Okay. Now, in case of ferrimagnetic, see if arrangement is anti-parallel, but their moments are different. This parallel, their moments is higher, than the this antiparallel down one. So, moments are smaller. So, there will be net magnetization, there will be net magnetization, magnetization will not be 0, and this is again for H equal to 0, this is again for H equal to 0. Okay. So, this way we can differentiate depending on the ordering of the permanent dipole moments in the material, we can differentiate the different type of magnetism, right. So, when we apply magnetic field on this, when we apply magnetic field on this, so what will happen? And if we vary the magnetic field, and if we vary the magnetic field, so then magnetization M, if it varies like this, depending on temperature, at different temperature, if we measure the magnetization as a function of magnetic field, so it varies like this, it varies like this, say this is T1, this temperature T2, this temperature T3, okay, where T1 is less than T2 is less than T3. Okay. So, in case of paramagnetic metal or paramagnetism, so magnetization varies as a function of magnetic field at different temperature, it is like this. Okay. In this case, this H and this magnetization, if it varies like this, I think one I can take straight line, then okay, if it varies like this. So, this t equal to 0, this curve for t equal to 0, this is T1, T2, T3. Okay. So, in this case also T1 is less than T2 is less than T3 is less than T3. So, here basically in this case this T2, so the T3 temperature here, its variation is similar to the here, okay. And above, if temperature is lower than this, even this T2 also here similar to T2 here, T3 similar here, okay. But above this that at T1 and T0, which are lower temperature than T2 and T3. So, here this we get some, it is not from 0, it is from here, it is from here. So, at 0 magnetic field, there is a magnetization. Okay. That is the difference of this between these two, and in this case, it is M and this is H for antiferromagnetic. It's similar to generally paramagnetic. It is similar to paramagnetic. Okay. it is similar to paramagnetic. Okay. In this case also T1, T2, T3, T1 is less than T2, less than T3. Okay. So, and this other case H and M, other case H and M. So, it's similar to this ferromagnetic, but magnitude will be different. Magnitude will be different. Okay. So, this T1, T2, T3. So, it is similar to this one ferromagnetism. Okay. So, at even 0 magnetic field you will get some magnetization depending on temperature. So, these are not good way to differentiate, these are not good way to differentiate them, but if you plot 1 by chi, if you plot 1 by chi as a function of temperature, then we will see this variation. I think I can draw one. Okay, this variation is like this. This variation is like this straight line, right? So, that we have seen earlier also for paramagnetic case. For ferromagnetic case, this is temperature and this is 1 by chi. So, you will get basically this kind of curve, if you, so this is Tc, it is Curie temperature, say above Curie temperature. So, it will follow the same paramagnetic behavior. So, it is started from 0, it will not start from 0. So, it is above this. So, sometimes this Tc, this ferromagnetic temperature, transition temperature we tell. So, it is exactly not this Tc, it is slightly lower, it is slightly lower, it is slightly lower. Okay. And then if you draw this, I think I should, it's like this. Okay. So, if you draw this, extend it, this straight line. So, this will be Tc and this called theta f. Okay. It is called theta f, this ferromagnetic transition temperature. Okay. But generally this difference between Tc and theta f is very small. So, thus we treat them as same, and in this case this 1 by chi and this temperature T, if you see. So, it's yes, it's like this. Okay. This is set a, so let me T here and this. So, there is a temperature, above that temperature it is like this, like paramagnetic one, Okay. So, this temperature is called nil temperature, and below this temperature Tn, below this Tc, okay, their behavior is different, Okay. But so, this one, if you extend this one, so this basically give the negative theta, this give the negative theta. So, it cut, this extension of this cut on this temperature at negative axis. Okay. So, for other case, it's like this, and if you take the asymptote, of this one, so it really cut the negative axis. Okay. So, in antiferromagnetic it cuts at negative, but at higher angle, and this for ferrimagnetic it cuts at negative asymptote, it cuts at negative, but it is smaller temperature. Okay. So, this is the feature of antiferromagnetic arrangement in ferromagnetic material, as well as this part it behave like this, So, this is telling this it has some ferromagnetic part also. Okay. So, this is the combination of ferromagnetic and antiferromagnetic. So, if you combine these two, so this presence of both are clearly seen here. Okay. So, this type of variation T, and this is basically T c, we tell T c, and this is M. Okay. So, this is the variation, of chi, 1 by chi, inverse of chi as a function of temperature, and if one measure this, so one can differentiate these 4 types of material. Okay. So, now question is these two material, ferromagnetic part and this ferrimagnetic part. So, these two also shows that this one shows that at this one shows the, I think I will additionally this one, if you apply, it shows if you without magnetic field, if you measure the magnetization as a function of temperature, okay. So, this we tell this M0 without magnetic field, MH magnetization as a function of magnetic field. Okay. Now, magnetic field is 0. So, I have written M0. So, M0 it shows this type of variation, this is T, this is Tc, okay, this magnetization. So, without applying magnetic field, you will see that the existence of magnetization up to the Curie temperature, but it's saturated one, and then it sharply fall down at the Tc. Okay. And also if you take the M as a function of H at T equal to less than Tc, so then what you see, this type of variation, hysteresis loop you see, okay. So, it has to be symmetric, it is not, I have not drawn correctly, I think I can put this way, yeah. Yes. So, this type of hysteresis loop we see, and in this case also the same behavior we see, okay, because it is basically it has two component, ferromagnetic and antiferromagnetic. Okay. So, here also in this case we see. Okay. So, this is the speciality of ferromagnetic material. You can differentiate ferromagnetic material from antiferromagnetic material immediately, right. If you see the hysteresis, now here this call basically so this is called the spontaneous magnetization, this is called the spontaneous magnetization without applying magnetic field. Okay. So, this what a magnetization we are seeing, that is the inherent one, the spontaneous one. So, spontaneous magnetization. So, this after applying field, this is called the saturation magnetization, MS saturation magnetization. This called remanent magnetization, MR remanent magnetization, and that means at H equal to 0 the magnetization remains, okay, it is not 0. To make this remanent magnetization 0, we have to apply field in opposite direction, and this much field we did to make it 0, So, this is called coercive field, this is HC, this is called the coercive field. Another things you can notice that, so above this, that whatever the magnetization that say spin up, that magnetization is in this direction, and below this magnetization negative, so it is down, okay, magnetization direction is down. Okay. So, above this HC, below, so below this HC, it is spin up or magnetization up direction, and when it is just H is higher than HC, so then it switch to the down. So, just HC plus minus del H, okay. So, you can take spin up or magnetization up, magnetization down, magnetization up, magnetization down. Okay. So, that is why HC is called also switching field, So, magnetization is switched from up to down near the HC field. So, that is why it is called also switching field. Okay. Okay. So, now we will discuss the origin of ferromagnetism. As we have discussed for paramagnetism, we will discuss about the origin of ferromagnetism, why this spontaneous magnetization exists, why remanent magnetization is there, why we need opposite field to make this remanent magnetization 0. So, that is we want to study. So, let us concentrate on the ferromagnetic material, Okay. So, now ferromagnetic material. So, there is a spontaneous magnetization, Okay. That means there must be internal field, there must be some internal field in the ferromagnetic material, right. So, so that we have to find out what is the origin of that internal field. Okay. So, Weiss basically Weiss proposed that propose that there is a magnetic field, there is a internal field in the ferromagnetic crystal, and that field is called molecular field, okay, or Weiss molecular field also we can sometimes we tell. And this molecular field is, because of this molecular field exists in the ferromagnetic crystal, and this field align the dipole moment, permanent dipole moment, even there is no external field. Okay. So, that is called basically Weiss model of Weiss model of ferromagnetism, Weiss model of ferromagnetism. So, Weiss propose or assume that there is a internal field, it is called molecular field, okay. And because of this field, without external magnetic field, the permanent dipole moment are oriented. And so from where this field is coming? So, he is thinking that you have a dipole moment, permanent dipole moment. Okay. So, many dipole moments surrounding of this one. Okay. So, what happens, this one, say ith spin or ith dipole moment. Okay. So, it feels magnetic field, it feels some field, okay, from because of the other neighbors, So, one can tell because of the interaction, among the dipole moments, okay, So, this is the origin of the molecular field. That means, so in case of paramagnetic material, we have considered that we have considered as a paramagnetic gas, where this dipole moments, permanent dipole moments are there, but they do not interact with each other, that we have assumed, that we have considered. And based on that, we have explained all the properties of paramagnetism. Now, to explain this ferromagnetism, Weiss considered that there is a internal field, and the origin of this field basically interaction among the dipole moments in the solid. Okay. So, because of this dipole moment, okay, there will be, it has whatever this, it will affect this one, will affect this one. Okay. So, this affect, the degree of affection, degree of effect, you can tell, degree of effect, Weiss assume that it is proportional to the, it will depend on the magnetization of this material. Okay. So, it is considered that this molecular field, if we write Bm, molecular field Bm, okay, internal field. So, this Bm is proportional to magnetization of this material, proportional to the magnetization of this material. So, this proportionality constant, you write this Bm equal to some constant say lambda. Okay. So, let me write here just Bm molecular field is equal to lambda m, where lambda is called this it's constant. It's basically it tells about the strength of the interaction among the dipole moment, strength of the interaction of the dipole moment. Okay. So, now what happens? So, this field already exists in the system. Now, if I apply external field, so external field B A, applied field B A, and already field exists lambda m m, this B m. Okay. So, that these moments. Okay. So, now we can consider this non-interacting moments like paramagnetic gas. Will fill this amount of magnetic field. Okay. So, that way that's the Weiss model. So, whatever this for paramagnetic gas, whatever the that's for non-interacting dipole moments, and whatever the expression formula we have derived. So, all formula will be valid for Weiss model of ferromagnetism, only we have to replace that magnetic field, external magnetic field B by this. Okay. So, what we have got for paramagnetic material, what we have got. So, this m by ms equal to below function is alpha, right, where alpha equal to alpha equal to g j mu b b by kbt, right, and ms saturation magnetization, ms is basically in number of atoms per unit volume in G J mu b. Okay. So, that is the saturation one, m, that is the saturation. I should write ms. Okay. So, this one. So, this was the result for paramagnetic material. Okay. Where Bj equal to, what was that? Bj alpha equal to 2j plus 1 below function by 2j plus 1 by 2j cot hyperbolic 2j plus 1 by 2j alpha, right, alpha. I think this I should write here. Here I will write alpha equal to alpha equal to Gj j mu b b by kbt. So, So then this was then minus 1 by 2j, 1 by 2j cot hyperbolic 2j, sorry, 1 by 2j alpha. Okay. So that's the result for paramagnetic material. Now, if I just this, as I mentioned that this, if I replace this B, B is here, in case of replace this B by this, then it is Weiss model, So, alpha in case of ferromagnetic material, alpha equal to Gj J mu V. So, B will be replaced by Ba plus lambda m divided by kBt, right. That is the alpha. Now, if external field, if I put external field B A equal to 0, means there is no external field is applied, okay, then alpha will be this lambda m kBt, right, when B A equal to 0. Now, from here I can get m equal to kBt alpha divided by Gj J mu V lambda, right. So, then if I write m by ms, just as a reference of ms. So, this what is ms? Ms is this. So, I will get divided by ms. So, I will get g square j square. So, I will get basically square of it lambda and then n. Okay. So, this is one expression we got, okay. Whereas, Bj equal to is this, okay. Now, if I plot, so this whatever we are doing, that is for Ba equal to 0. So, this we are doing now for Ba equal to 0, for this case, okay. Under this condition, whatever we will proceed. So, here one thing is, so Bj, what is this? It is equal to basically m by ms. So, here you see m by ms, that is a function of here alpha, okay. And here m by ms, it is a function of alpha, okay. So, we will get simultaneous solution if I draw both curve, the simultaneous solution will be the intersecting point of these two curves. So, if I plot this as a function of alpha and this m by ms. So, for below function, if you plot the below function, the curve of below function is this basically, curve of Euler function is this. So, this is Bj of alpha, this curve. Now, if you draw this one, so as a function, so this basically for different temperature, it is for a particular temperature, it is straight line. Okay. Now, you will get straight line like this, you will get straight line. I think I should. So, let me just this once if I draw. Okay. So, this will go basically this way, this will go this way, this will go this way. Okay. And if I draw another flat one, I think this is not the right one. So, okay. So, these are different temperatures. This temperature is say this is T1, this is T2, this is T3. Okay. This is T1, T2, T3. Okay. So, here T1 is less than T2 is less than T3. Okay. So, T3 it is not intersecting this curve, it is not intersecting this curve except this at alpha equal to 0 where ms is 0. So, we do not have interest for this solution, and T2 it's a basically it's the gradient, it's a gradient of this Bj curve at alpha equal to 0, and this other one it's below T2 temperature. So, it is intersecting at 3 points, this and this. Okay. So, it will have plus minus value, it will have plus minus value, okay, plus minus value of m by ms and also 0 value. So, we are not interested about this 0 value, alpha equal to 0 ms value. So, here from this curve you can see that below a certain temperature there is the exist of magnetization, there is the exist of magnetization, right, because it has now solution, simultaneous solution for which is satisfying this as well as this one. So, this gradient is basically T equal to is the Tc, critical temperature, transition temperature. So, above Tc, T3 is above Tc. So, it has no solution, it is not intersecting, and below Tc at T1 it is intersecting. Okay. So, thus this Tc is the transition temperature, above this temperature it is paramagnetic and below this temperature it is ferromagnetic, because there is magnetization exists even at external field 0, even at external field 0. So, this temperature Tc is basically one can find out this Tc. So, that will do. So, this Tc at T equal to Tc, this gradient of this straight line and this gradient of this Bj curve at alpha equal to 0, they will be equal. Okay. They will be equal. So, from that condition one can find out the relation between the T c and the this lambda. Okay. So, that I will continue in next class. Let me stop here. Thank you.